Lecture 7, Global Circulation of the Atmosphere, Chapter 5. What we're going to be looking at is something that looks very complicated, the circulation of the atmosphere with pressure and winds. But what we're going to do is take this really complicated system on Earth, and we're going to make a model out of it. We're going to simplify this complex reality. And what we're going to wind up seeing, what I like to do is give you the conclusion to show you how really simple this can actually wind up being. And what we're going to be doing is we're going to be looking at particular lines of latitude, and we're going to be looking at simply increments of 30 degrees, 0, 30, 60, 90. And what we're going to wind up seeing is alternating pressure and wind belts along lines of latitude. And so let's see this unfold. Like I just mentioned, in our simple model, we're going to be seeing pressure systems dominating along, these 30-degree increments, and they're going to wind up being alternating. And then because we've got, highs and lows, we're going to set up pressure gradients and winds. Let's start at the equator. Now, on any one day of the year, low pressure is going to dominate along the equator, and we're going to create a belt of low pressure systems. So on any one day of the year, there'd be a whole series of low pressure systems with isobars, circular isobars showing the low pressure. Now these are called the equatorial lows, or the equatorial low pressure belt, lined up right along the equator. Now this pressure belt is set up by temperature. All right, remember, there are two ways to set up highs and lows: by temperature or by getting the air to flow in the correct direction. And so we know what it's like temperature-wise at the equator. It's hot all year long. All right. And so here we've got, what I'm doing here on the right side is we're kind of tipping the troposphere on its side. What we want to represent is, rising air, that hot air rising all the time, all year long at the equator. And we know that rising air creates clouds and rainy conditions. And so the low pressure system, the low pressure belt, creates very rainy conditions all along the equator, with this rising hot air and creating clouds. Yeah, and as it turns out, the tropical rainforests, very rare rainy locations on Earth, line up right along the equator. All this rain and creating the tropical or equatorial rainforests on Earth all along the equator are set up by the equatorial low pressure belts over the continents. Yeah. All right, again, in our model, we're just looking at 30-degree increments. And so at 30 degrees north and south, we're going to have an alternating pressure belt. That's what our conclusion is. So if we had low dominating at the equator, we're going to have high dominating at our next increment of pressure belt. Now, this high pressure is just outside of the tropics, so any location just outside of the tropics is called subtropical. And so these are called the subtropical highs. And on any one day of the year, all along 30 degrees north and south, you will likely see on a weather map a whole series of high pressure systems, all along 30 degrees. And again, I just randomly put in a whole series of H's in both hemispheres along 30 degrees north and south. Now, high pressure here is set up mechanically by getting the air to flow in the correct direction. It's not at all set up by temperature. And what's going on here is at the equator, you've constantly got that hot air rising all year long. And it can only rise to the top of the troposphere. It can't rise into the stratosphere. No weather takes place there. And so all of this rising air winds up having to spread out laterally away from the equator at the top of the troposphere, around 8 or 9 miles up. Now, what winds up happening, 2,000 miles away, around 30 degrees north and south, that the original push kind of dies on out. So you got the original push of rising air pushing the air laterally at very high altitudes. By the time you get to 1,000 or so miles away from the original push, the upper air winds start to slow down, all right, and start to pile up. And there is a tendency for this originally rising air to start to sink at 30 degrees north and south. So this is set up mechanically, so you wind up with a belt of sinking air and in the subtropics, and so it's called the subtropical high pressure belt, and we often abbreviate it STH for subtropical high. And yes, so high pressure sinking air it creates cloud-free conditions. And so, the great deserts, the big deserts on Earth are definitely subtropical high deserts set up by high pressure, clear skies, day in and day out. Now, I'm not saying that every place along 30 degrees, is a desert. Of course, we're not. And we're not a desert because, well, we've got the Gulf of Mexico. Right? If we didn't have that, if we had land to the south of us, we'd be a desert. But we've got the Gulf of Mexico that pumps in moisture. But the southwestern United States, is a desert, and it is set up, by high pressure. It is definitely, a subtropical high desert. Really, the greatest deserts on Earth. If you think about it, the Sahara, Arabian, and the deserts of the Southwest Asia, all set up by high pressure in the subtropics, subtropical high deserts. Another really great example is basically the continent of Australia. And here's 30 degrees south. Beautiful example of subtropical high desert conditions in Australia. Another really good example, a little bit off, but it still works out, is in southern Africa. The Kalahari Desert is indeed a beautiful example of a subtropical high desert, high pressure and cloud-free conditions. The Patagonian Desert is a little bit off, but it's still a pretty decent example of a subtropical high desert. So that's where the great deserts of the world are. All right. Now, so since we've got, low pressure dominating at the equator all year long and high pressure really dominating, at most locations along 30 degrees north and south, we are going to set up permanent pressure gradients. We're going to create permanent winds. And let's start with the northern hemisphere, and then I want to move on to the southern hemisphere. But we're going to set up winds of the tropics, and the winds of the tropics are called the trade winds. That's our tropical wind belt, and they're called easterly winds. And in talking about winds or naming winds are always named from the direction in which they're coming from. And these winds, the trade winds that I'm going to show you in just a second, are always originating from the east, and they wind up blowing west. So they're called easterly winds, the trade wind easterlies. Let me show you how they're set up. I don't really have my highs and lows lined up perfectly, but we've got a high pressure belt and a low pressure belt, and so we've got a dome of high and a trough of low. And we're going to set up a permanent pressure gradient out of the high into the low, from 30 degrees to the equator. So this is large scale pressure gradients and large scale wind belts. Now in the northern hemisphere, our pressure gradient, our direct flow out of the high into the low, is diverted by the Coriolis effect, and we're going to wind up being deflected in the northern hemisphere to the right of the pressure gradient. And right, so what you've got to do is you've got to look upside down, right, and you wind up with your rightward deflection. And so what we're going to wind up with are winds that are originating in the east and blowing west. Now specifically, when you look at the real diagram that we're recreating here, these are called the northeast trades. See, they're originating in the north and in the east, right? But anyways, we're just going to call them easterlies. And then in the southern hemisphere, again, you've got permanent pressure gradients set up out of the high and into the low. But again, the Coriolis effect is going to deflect the wind in the southern hemisphere to the left. So you can see this easier because we're not upside down. And so we're going to deflect that pressure gradient to the left of its intended path. And again, we've got our belt of trade winds in the southern hemisphere, dominating the tropics. Now, these are specifically called the southeast trades. They're originating in the south and in the east. But again, we just simply call the trade winds easterly winds, originating in the east and blowing west. Originating in the east, blowing west. All right. And so what we're able to do now is kind of at the Earth's surface put in, the winds blowing out of the high and into the low back to the equator. And so that helps to kind of, reinforce the push of the rising air. And let me just give you the term for that when you've got the trade winds meeting and actually, reinforcing the rising air, creating really rainy conditions. So let me talk to you about the name of that feature. That's called the Intertropical Convergence Zone, and it is a mouthful of a term. And it's often abbreviated ITC, Intertropical Convergence, or ITCZ, Intertropical Convergence Zone. And it's usually found near the equator, and it represents the exact meeting of the trade winds. All right. And it's usually somewhere near the equator. And so the winds converge, they're meeting exactly. And where they're meeting exactly at the Earth's surface, it's going to force the air to rise. And in conjunction, converging winds forcing the air to rise near the equator. And so it's going to work in conjunction with the hot air rising already. And so if you've got the Intertropical Convergence Zone meeting up with the equatorial low, whoa, is it rainy. I mean, you're going to wind up with hundreds, 200, 300, 400 inches of rain per year. Tremendous amount of rain. So you've got two things working together to get air to rise and create thunderstorms. On a satellite image, I mean, you can actually see the Intertropical Convergence Zone. I can always pick it on out as a line of thunderstorms, somewhere near the equator. So these are all, this is the Intertropical Convergence, with the exact meeting of the northeast trades and the southeast trades converging at the Earth's surface and literally forcing that warm air to rise and create thunderstorms. So it's a rainy location on Earth. So now what we're going to do is we're going to finish off our alternating pressure belts at 60 degrees and 90 degrees. So it's not really as hard as you think. It's alternating. So at 60 degrees, it's going to be low pressure. And it's called the polar front low. And low pressure is always rising air and bringing clouds and rain. And the word front here is really kind of critical. We're at middle latitude locations where we get cold fronts and warm fronts and stationary fronts. And we're going to learn more about fronts in an exam too. Material is building. I can only do one step at a time. But when we get a front moving through, it brings rain. And really what fronts are low pressure systems. And so you wind up with rainy conditions associated with fronts, in mid latitude locations, somewhere around 60. This one maybe 40, 50, 60. It's a little off maybe. And the same thing is true in the southern hemisphere. And then our final belt, well, it's not really a belt. I mean, it's a center of high at the poles. And it's called the polar high. Now, high pressure, the air is always sinking. And so you wind up with clear conditions. So it's really quite dry at the poles. And so we've got the polar high. And so we've got alternating pressure belts in increments of 30 degrees. Low, high, low, high. All right. Now what we're going to do is we're going to finish off the wind belts. And they're going to be alternating. We had easterly winds, the trade winds of the tropics are easterly winds. Guess what? We're going to have westerly winds and then easterly winds. And so everything is going to be alternating. All right, yeah. So now in the northern hemisphere, let's look at how the westerly winds are set up. Now, these are the dominant winds of middle latitude locations, between about 30 and 40, 50, 60 degrees. Yeah, and so in the northern hemisphere, what we wind up having is our high pressure dominating at around 30 degrees, and then we've got our low pressure trough, somewhere at higher latitudes around 50 or 60 degrees. And so we're going to set up a permanent pressure gradient out of that high into the low. But because we're in the northern hemisphere and the Earth rotates, that pressure gradient, the winds are not going to flow that direction direct. They're going to be deflected to the right. All right. And so we wind up with a dominantly westerly wind belt. The winds are coming from the west and blowing east. And the same is true in the southern hemisphere. You wind up with westerly winds of middle latitude locations. Again, I'm not lining up perfectly, but we've got our dome of high and our trough of low and our direct pressure gradient. But because the Earth rotates, we're going to deflect to the left, so you got to again turn yourself upside down and deflect to the left. And so we wind up with winds coming from the west and moving east. Yes. And then, let's do the same thing for the other wind belt, the polar easterlies. Again, you've got the high pressure dome and the low pressure trough. You're going to set up a direct pressure gradient. In the northern hemisphere, they're deflected to the right. And again, you got to kind of turn yourself upside down to see that rightward deflection. And so you wind up with very, very cold winds, kind of blowing out of the poles, but they're kind of coming out of the east, and so they're called the polar easterlies, right, coming from the east and blowing west. And then the same thing in the southern hemisphere. You've got your pressure gradient out of the high into the low, and then you can easily see the deflection to the left in the southern hemisphere. But you still wind up with winds kind of coming out of the east and blowing west, and so these are called the polar easterlies. All right, I always like to show where we are in the whole scheme of things. And we, meaning the United States. The United States and Europe are mid-latitude locations in the northern hemisphere, dominated by the westerly wind belt. And so, you can always see weather systems coming in off the Pacific and, moving west to east across the United States. So it really is a really common pattern to see any weather systems moving and being directed by the westerly winds of mid-latitudes. All right, let's talk about what sets up the high pressure at 90 degrees and what sets up the low pressure at 60 degrees. Let's start with the easy one. At 90 degrees north and south, this pressure system, the high pressure, is set up by temperature. All right. And so what do we know about temperature at the poles? It's very cold. So this is the opposite of what's going on at the equator with heat rising. Here we've got incredibly cold, dense sinking air dominating all year long, creating high pressure. And high pressure with sinking air creates cloud-free conditions, and the poles are quite dry. And so let's move on now to our final pressure belt at 60 degrees north and south, and it's the low pressure belt. And remember, I was emphasizing the term front. So in mid-latitude locations, it really is the only place on Earth where you've got the meeting of opposite air masses. You've got, cold polar air that can move on down to middle latitudes, while at the same time you can have warm tropical air, moving into mid latitudes. And where you've got the meeting of opposite air masses, it creates fronts in mid latitude locations. And that whenever there's a front, we usually get rain, but it does represent a trough of low. And we'll talk more about that. Now, in the side view here, okay, I want to show you the warm air moving out of the subtropical high and into the polar front low. This is warm air coming from the tropics, meeting cold air coming out of the high and into the polar front low, cold air. All right, and so where we've got warm and cold air meet, you're creating a frontal system. And cold air meeting at a front, it's always going to be the warm air that's going to be forced to rise. And then you're going to wind up creating clouds and rain associated with the passage of a front. And so we'll be talking a lot more about fronts for exam too. All right, we can only do things stage by stage. And be aware of the fact that this is the only place on Earth where you've got the meeting of opposite air masses. It's just all cold at the poles. It's all warm within the tropics. And again, mid-latitude locations. And I can do the southern hemisphere here too. We've got warm air moving out of 30 degrees, and then cold air moving out of the poles, and they meet, create a front, and the warm air is the one that's going to rise and create clouds and rainy conditions associated with the front. So we've just completed our model. And there it is. They've got a few things that we're not really have to worry about. But, they've got the front put in, and they've got our subtropical high pressure belt and the equatorial low, and so they've got all of that there, and the winds and things like that. And so we've kind of done this in a little bit more of a simplified manner. All right. So it's a good model. I mean, what a model is a simplification of reality, and that's indeed what I've done. For the test, make sure that you study the practice fill-in-the-blank questions in regards to this global circulation of the model, because that'll guide you for what you'll need to know for the test. And you'll see that it's pretty straightforward. You might be frightened by the model, but once you go over the actual questions that I'll be asking, they're really quite straightforward. So make sure you study in that manner. I've got another thing to do to you, so this is going to be another 10 or 15 minutes long. So what we're looking at here is the actual situation of high and low pressure systems in January. So it's in the northern hemisphere. It would be winter in the northern hemisphere. And then we've got a July map, all right, of the actual pressure systems that you would find in July. And again, it's summer in the northern hemisphere. And what we're going to wind up seeing, I'm going to kind of take a look at it, is that in the southern hemisphere, now remember the southern hemisphere is mostly water, and it's called the water hemisphere. And as it turns out, the belted arrangement, of low, high, works out to be perfect in the southern hemisphere. The model is perfect because we don't have, big land masses heating and cooling to disrupt our nice belted arrangement. So in the southern hemisphere, it's perfect. Here we've got the intertropical convergence zone and a whole bunch of low pressure in green near the equator. And then look at the subtropical highs lining up right at 30 degrees south. Subtropical high. Now here the green represents low pressure, of middle latitudes. And this is not like a surface weather map showing fronts, but there would be cold and warm fronts moving on through here in the southern hemisphere. And they're not showing the polar high here, and the same thing is going on in July. There's the intertropical convergence zone, the belt of low pressure shown in green, the beautiful stacked up arrangement of the subtropical highs at 30 degrees. And then we've got our polar front low, and again, it's not showing the frontal systems, but of mid-latitudes. And again, it's not showing the polar high. But the belted arrangement is great in the southern hemisphere. Now, the big problem, all right, is the northern hemisphere. Now, the model is good, and you absolutely need to know the model. But you also need to be aware of this fact, that in the northern hemisphere, the land hemisphere, we've got large continents like Eurasia and North America that heat up to a high temperature in summertime and cool down tremendously in wintertime. And this heating and cooling of the land in relation to the oceans wind up disrupting our nice belted arrangement. So you need to know the arrangement, but you also absolutely need to know what's going on in the northern hemisphere in January to our belted arrangement. You see it's all kind of messed up here. And then you need to know what's going on in July in the northern hemisphere with our belted arrangement. And so what we're going to do now is focus on the northern hemisphere. And what you got to do now is remember what we talked about with the marine effect and the continental effect and the heating and cooling of land and water. All right, so this is going back to that lecture. And what we're going to do is we're looking at the January map, and we just really want to focus on what's going on in the northern hemisphere. Now, for this class, this is the January air pressure map. For this class, we're only going to focus on the high pressure systems that develop seasonally in the northern hemisphere. Just the high pressure. Now, in my upper level meteorology class, we do it all. But for this class, we just need to know the high pressure systems. Now, remember high pressure, all right, is set up by cooler air. All right, so you've always got to think of the season. The season is January, and what surface is going to be colder to create cold, dense, sinking air. And so in January, what is going to be colder? Is it the land or the oceans? Remember, the oceans don't really cool down that much. They stay pretty warm. And so definitely, we're just going to focus on the highs, and definitely the land masses are getting very cold in January. And so every winter time, really intense high pressure systems develop over the extremely cold land masses. And some of the highest pressure ever recorded on Earth occurs over Siberia, that gets intensely cold, and intensely cold, dense, sinking air can create some of the highest pressures ever recorded on Earth. So every winter time, right, we see the development of a very intense high pressure system really dominating Asia, and it's called the Siberian High because it's centered over Siberia. Now, over North America, it's not as well visualized on this one map, but over Canada, Canada gets very, very cold in winter time and sets up a high pressure system that we call the Canadian High. And we get Canadian High weather in winter time, after the Canada is getting really chilled down and the cold air starts to spill southward behind a cold front. And after the cold front moves through, we get cold and dry air. And so, for many, many days during the winter months, behind a cold front, we'll actually experience the weather of the Canadian High, if it moves southward and expands. And so you need to be aware of the high pressure that develops over the land masses and their names in January. All right, we're not going to worry about the names of the low pressure system. Now let's look at summertime in the northern hemisphere. All right, and again, we're just focusing on the big high pressure systems that develop. Now, again, you got to think of what surface is cooler in summertime. All right, and indeed, it's the oceans. The land masses are really heating up, but the oceans are kind of staying the same, and really intense high pressure systems develop in the northern hemisphere, in the northern Atlantic, in the northern Pacific, over the relatively cooler oceans. And they develop every summer, and they're given names. And here, in the Pacific Ocean, centered over, the Hawaiian Islands, the Hawaiian High enlarges and intensifies over the Pacific Ocean every summer. And so that's called the Hawaiian High. Now, in the North Atlantic, we have a high pressure system that's set up, and it's centered over Bermuda. Now, this high pressure center has two different names. A lot of times things, have a couple different names. Now, on this map, it's the Azores High. We here do not call it the Azores High. We call it the Bermuda High. And whenever the meteorologists on TV are referring to the Bermuda High and how it's impacting the eastern United States, that's what they call it, the Bermuda High, and we call it the Bermuda High. So on the test, we're going to call it the Bermuda High that dominates in summertime. It grows and enlarges and really becomes well developed, right, by the time July comes around, and August, right, and even into September. It's still pretty much, summer. So we've got the Bermuda High. Now, the thing is, these high pressures are centered around 30 degrees north latitude. And these are the best that we're going to do in the northern hemisphere to have high pressure in subtropical latitudes. All right. Here we've got our belted arrangement at 30 degrees south of the subtropical highs. And they just exist all year long, no matter what. You just saw it back in the January map. There they were, all right? But here, this is the best we're going to do in the northern hemisphere for high pressure in the subtropics. So the Hawaiian High and the Bermuda High that really intensify in summer are the subtropical highs for the northern hemisphere. Right? They're still there in winter time, but they're smaller and less intense, but really become very, enlarged and intense. And that's the best we're going to do. So these are the subtropical highs for the northern hemisphere. All right. I've got two more topics that I want to talk to you about, and these are very much related to the setup of high pressure and low pressure over the land and water in the northern hemisphere. So you say, oh, why is she talking about monsoons all of a sudden? It's very much related to what I've just been talking about. And so I want to talk about what a monsoon is. And the monsoon is really well developed over South Asia. And so we're going to be focusing on India and South Asia. And what a monsoon is, this is the real definition of it. It's a seasonal reversal of wind direction. That's what it is. Now, a lot of people think that a monsoon is just, like, really intense rain or hurricane-like weather. No, the definition is a seasonal reversal of wind direction. And that rain is really only half of it. All right, it's really only half of it. But the word monsoon means season in Arabic. Means season. And so we're going to be looking at what's going on in southern Asia, particularly India. And so in India or South Asia, there are two seasons or two monsoons. And I'm going to begin with the winter season or the winter monsoon. And we know in wintertime, Asia is dominated by the Siberian high. All right, in wintertime, the landmass is incredibly cold. And so we know that winds in the northern hemisphere blow out of the high and in a clockwise manner. And so we're looking now at the winds blowing out of the Siberian high, in the southern portion in India and Southeast Asia. So during the winter months, all right, we're dominated by the Siberian high. And when we're looking at India, the winds blowing, coming from the north, they're northerly winds, all right, during the winter months. And these northerly winds are coming out of Siberia. And so this is the cold and dry season. So there is a dry monsoon. I mean, the winds are coming off of a continent, and so they're not picking up any moisture. So this is the cold and the dry season for South Asia. Now let's move on to the famous summer monsoon. All right, and so here we've got the picture in July, let's say, and so the landmass of Asia, all right, gets really, really superheated in summertime, and a low pressure system develops over the superheated land. Now, we didn't give the names here, but it is called the Asiatic low. There's the low pressure over the superheated land. And now, of course, the Asiatic low, this low pressure system, is not going to form at the exact same location as the Siberian high. Remember, it's all temperature related. So it's colder farther north, so that's where the center of the Siberian high is going to be. And the center of the low is going to be, in the tropics, right? In lower latitudes where you've got more heating. And so that's why the location of the high and the low aren't in the same place. So you've got, more heating and more intense low developing. All right. But anyways, you got low pressure developed during the summer months over the heated land. And what you wind up with is you got to remember the circulation in the northern hemisphere around a low pressure. Remember, the winds are always blowing inward, all right, but in a counterclockwise manner. And so you kind of take a look at the winds, coming into that low, and the direction of the winds over South Asia or India, and the winds are coming or originating from the south, and so it's hot. I mean, because they're in the subtropics, quite close to the equator, and it is a very rainy season. I mean, so you've got warm, moist winds coming off the Indian Ocean, the tropical ocean, pumping in moisture, and once that moisture moves on land, it forms clouds and thunderstorms and rain. And take a look, so they've got the precipitation bar graph for this one location, and actually, I guess it is in India. And take a look at how dry it is during the winter monsoon, an inch or so of precipitation during the winter months, and then bam, all right, look at the summer monsoon, all right. Can you imagine getting over 120 inches of rain in a month? That is incredible. Now, in Thibodeau, all right, we get 4, 5, 6 inches of rain per month. Now, if we have a really incredibly rainy month, or a hurricane in a month or some horrible event, we might get 8 or 10 inches, max. All right, 8 or 10 inches. Okay, all right. I mean, that's about as high as it ever gets for us. Can you imagine 120 inches So, I mean, that is tropical moisture. And so that's the summer monsoon. All right. One final topic, right? Very much related to highs and lows, and this is particularly the subtropical highs. And I want to focus on ocean circulation. So, the ocean currents are pretty much set up by winds. The winds, pushing the surface of the ocean, create ocean currents. But I want to focus on one particular type of ocean circulation. They're called gyres. They're gyres, and they're ocean basin circulation loops. And so we're just going to focus on the North Atlantic and the South Atlantic basins and the gyres that are set up there. But they're also in the North Pacific and the South Pacific. I'll show you that in another diagram. Now, these gyres are set up by the outblowing winds of the subtropical highs. Now, in the southern hemisphere, remember, they're unnamed and they just exist, all year long. And they exist over the, southern Atlantic. And now remember, you've got to remember the direction of the circulation of high pressure in the northern and southern hemisphere. We know that the winds are always outblowing. It is kind of critical that outblowing winds can actually start the ocean to stir, all right? And it's always going to stir in the direction of the circulation of the high. And so in the northern hemisphere, we know that high pressure moves in a clockwise CW manner. And so in the northern hemisphere, our subtropical high really develops in summertime and really gets this gyre going. And our subtropical high is called the Bermuda High. Now in the southern hemisphere, it's unnamed and it just exists all year long. But in the southern hemisphere, remember, high pressure moves in a counterclockwise manner. So that's going to stir the ocean and create a counterclockwise gyre. All right. Okay, and so what's going to wind up happening, right, by the pattern of the circulation of these gyres is it's going to wind up always setting up, this is what we're going to look at, warm and cold ocean currents. And let me start with east coast of continents, and I'll show you this a little bit better on Earth in just a second. But if you're on the east coast of a continent, you should always expect a warm offshore current. And let me show you how it's set up. Let's look in the northern hemisphere. And so we've got our clockwise gyre set up by the Bermuda High. And what we've got here is, kind of tropical winds here. Here we are, around 20 degrees north, warm water, and what winds up happening is the warm water is being pulled in a clockwise manner, all right, up the east coast of the United States. And so we've got tropical waters pulled on up, and so we wind up creating a warm ocean current along the east coast of the U.S. And then by the time, the gyre makes it on up to the North Atlantic, it's pretty cold up here, and so we're going to continue our gyre now from the northern Atlantic, and now we're going to move along the west coast of Europe and the west coast of Africa. And so we've got cold polar waters here, and those cold waters are going to be pulled southward, all right, with the direction of this gyre. So we're always going to wind up with cold ocean currents on west coast of continents. And it works out the same for the southern hemisphere. Because of the reversal of direction, again, on the east coast of South America, here's, Brazil and Argentina, you've got warm tropical waters being carried in this counterclockwise flow when you create a warm ocean current along the east coast of South America. And then we've got cold Antarctic waters here. And again, what you're going to wind up doing is taking these cold Antarctic waters in the circulation of the gyre, and we're going to wind up creating a cold offshore current on the west side of Africa. All right. So we're always going to wind up with cold ocean currents on all west coasts of continents and warm ocean currents on all east coasts of continents. Yeah, and this is my diagram. I mean, I've just drawn in the major continents in each hemisphere, and I've drawn in the Atlantic Ocean and the Pacific Ocean, and I put in our named high pressure. There's what we get for our subtropical highs, the Hawaiian high in the northern hemisphere, and we're going to wind up, with this clockwise circulation. We're going to get cold Pacific waters being brought along the western coast of the United States, and we get a cold current. Now, this one is called the cold California current here. And then you wind up continuing the direction of the clockwise circulation, and you're getting warm tropical waters being brought northward. And over here is China and Japan. And so you wind up with warm waters being brought along the east coast, all right, of China. And it's called the warm Japan current. All right. And in the Atlantic Ocean, we've got our Bermuda high. That's our subtropical high. And again, we've got a cold current moving along the west coast of Europe, and it's called the cold Canary current. And then we've got our warm waters and our warm ocean current. And you should be familiar with the name of this one that moves along the east coast of the United States. It's called the warm Gulf Stream. All right. And then in the southern hemisphere, because of the reversal of the direction of the circulation of the high pressure, it works out that we still wind up with cold ocean currents on west sides of continents. It works out nicely. And we still have warm ocean currents on east sides of continents. So like I just showed you in the South Atlantic, you've got cold Antarctic waters in the circulation being brought upward. And this is called the cold Benguela current. Then we warm it on up here in the tropics, and we've got the warm Brazil current being brought from the equator southward. Then in the unnamed subtropical high in the southern hemisphere over the South Pacific, again, we've got cold Antarctic waters being brought up. And so on the west side of South America, we've got the cold Peru current. It's also called, it has two names, or Humboldt current, but it is a cold, very cold current from Antarctica. And then you wind up with it still moving and rotating around that subtropical high, and you're taking warm waters and you're bringing them along the east coast of Australia, and it's called the warm Australia current. All right. And so here you can take a look at this in a little bit more detail. They've got the names of the currents, the Benguela current, the Brazil current, the Gulf Stream, the California current, and and the Kuroshio. That's the Japan current that I just mentioned. But you really should know the names of the cold and the warm ocean currents that dominate the east and the west coast of the United States. So off the east coast of the U.S., we have the warm Gulf Stream. And so when you go swimming, it's, really warm waters here on the east coast. But on the west coast of the United States, even though California, the west coast, is very, very famous for its beaches, the waters are very cold, are really quite cold, with the cold California current, with the North Atlantic waters being brought around the Hawaiian High. And, surfers or people that are going to spend some time, swimming, you've got to wear rubber suits, you've got to wear wetsuits, because the water is surprisingly cold all along the west coast of the United States. End lecture 7.